each of these pieces of software here at ShmooCon, and you can download them whenever you like. We'll talk about some visualizations of data provided by the Honeynet project, and those visualizations are constructed by using psad to parse iptables logging data and then send that output through a project called Afterglow, which is written by Raphael Marty to render graphical representations of the data. And there will be a live demo. I've got the terminal settings up, but if you in the back can't see, you may want to try to move forward a little bit at the demo if you want to try to see everything. And leave time for questions at the end. So, implementing IDS infrastructure, why do we need another IDS? Well, we don't need another IDS. There are lots of really great ones out there. Snort being the 800-pound gorilla in the open source world, of course. There are lots of commercial implementations as well. But IDSs themselves can be targeted both from the detection standpoint as well as the code execution standpoint. For example, the Snort DCE RPC vulnerability a couple months ago is an interesting example. And you can also think about a modified version of the old stick and snot tools to send faked attacks over the Tor network. And that's an interesting example where the stream preprocessor was written, of course, in Snort to mitigate the capability of an attacker just to craft a packet that contains malicious-looking application layer data as far as what the Snort rules language was defining as malicious, and then maintain a notion of combining the signature detection with the notion of connections, the connection state, and that mitigated the original stick and snot tool style attacks. But these types of things are not going to go away, and you can envision application layer encodings that are challenging even the Snort rules language. Intrusion detection systems have their work cut out for them, I would say. So defense in depth is important. If there is another mechanism for helping to detect attacks in an effective way, it makes sense to use it. And in the case of iptables, by combining the StreamMax extension with the Netfilter connection tracking modules, you can get host fragment reassembly for free, essentially, and that will be something I'll talk a little bit more about later. So if we're interested in trying to come up with some functionality for intrusion detection, we have some requirements, right? First and foremost, signature-based packet inspection. We should be able to inspect both packet headers and application layer data. The Snort rules language defines lots of signatures for both, of course, the majority emphasizing application layer data. We would like to have network layer and transport layer reassembly if possible. We will see that network layer reassembly is easily accomplished with iptables. Transport layer reassembly we are not going to get. However, we can match against connection states and combine those states with Snort rules that have been translated into iptables rules, and that allows us to mitigate the original stick and snot style attacks in the same way that Snort did, at least by matching the connection state. Reporting, of course, we need to be able to have some way of generating events. If an IDS sees something, it's not enough just to be able to detect it if you can't alert on it. And in something that's a nice consequence of being a firewall, and therefore inline by definition, is that iptables can respond to attacks, and I emphasize this is an optional capability. Okay, so Snort, of course, widely accepted and deployed rules language for detecting malicious activity on a network. There are lots of ways to acquire very updated rule sets. Bleeding Snort is a nice rule set that's a BSD licensed set of signatures, very frequently updated. And in a vote of confidence for the Snort rules format, you have things like iDefense and Endeavor Security, which provide signatures for new attacks that they're seeing in what? In Snort format. So it defines a good direction for an IDS language to emulate, if we can, within iptables. So the question becomes, how much of the Snort rules language can we legitimately emulate within iptables itself? So with iptables, you can specify granular packet header tests This essentially allows us to characterize the Snort header portion of a Snort rule, which we'll cover in a little bit. You can match against connection states and combine that those matching with the Netfilter connection tracking modules. And the way we do application layer detection in iptables is with the string match extension. String matching was first introduced in the Linux 2.4 kernel series as a patch, which was distributed by the Patch-O-Matic project by Netfilter. But it had some significant issues. Late in the 2.4 kernel series, the kernel developers made a fundamental change to something called an SK buff structure, which is a socket buffer structure within the kernel used to represent socket data. They made a change in, I think, around 2.4.30 or so to make it such that these SK buff structures no longer had to lie on blocks of contiguous memory. And the original string match extension assumed that application layer data associated with SK buff structures lied on contiguous memory, and because there wasn't anyone around to port the string match extension to the new SK buff structure style, it effectively broke late in the 2.4 kernel series. And that remained the case all the way through the 2.6 kernel series until 2.6.14, and that was when the string match extension was rewritten to make use of the new SK buff style data structure. And it was rewritten with sort of with a vengeance, you might say. It now supports multiple algorithms via a text search infrastructure in the Linux kernel. There are currently 3 algorithms supported, I believe, the 2 most notable being the Boyer-Moore algorithm, which is commonly used by intrusion detection systems, and also the Knuth-Morris Pratt algorithm, which is not used so much because it doesn't typically have as good performance characteristics as Boyer-Moore. And a vote of confidence for string matching and iptables, if you look at recent Linux kernels downloaded from kernel.org, you will see that the string match extension capability is essentially compiled in by default. So if you're running a recent kernel, there's a very good chance you already have this capability, and you don't have to go through a kernel compilation process in order to take advantage of it. You may just have to issue. The question is define recent. I believe that it is enabled by default as of about 2.6.18, approximately. The port was made available as of 2.6.14, but I don't think it was enabled by default at that point. So when you combine Netfilter connection tracking with the string match extension, you essentially get network layer defragmentation for free. And this is a nice consequence. If you look at the frag3 preprocessor in Snort, you will see that you can tune the algorithm that Snort uses to defragment network layer traffic. That's important because various IP stacks out there have differences in how they assemble network fragments. So suppose you're running an IT infrastructure and you deploy a Linux machine on within a range of IP addresses that's normally reserved for Windows machines. Well, if you didn't communicate this information to your security infrastructure, your security group, so they can reconfigure the frag-free preprocessor so they can run the Linux defragmentation algorithm against that particular IP address, now Snort is going to reassemble traffic according to how a Windows IP stack does it, and so there's a disconnect there. If you're running iptables and a server on a Linux system running iptables, you don't have to worry about that because you are taking advantage of the defragmentation algorithm of the actual IP stack on the system. So I'd like to say a couple of words about active response and intrusion prevention. There are plenty of reasons not to use any kind of response mechanism for network traffic for lots of reasons. False positives, the ability of an attacker to abuse the system potentially, and the possibility of fingerprinting the response mechanism itself. Simple Nomad talked about that in one of his recent talks, I believe. However, you can envision some scenarios where controlling the shape of application layer data that can talk to a local socket is a good thing. There are many attacks out there that because the target environment is so rich, they don't have to worry about, obfuscating themselves through network defragmentation or TCP session splicing or taking advantage of encryption. It just doesn't matter because there's so many things to attack. They don't have to care. The 2% of the networks out there that are really protected that actually use intrusion prevention in an effective way for those particular attacks, well, they say, you know what? I still got 98% of all the targets out there to attack, so I don't really have to care about that 2%. So you can envision a scenario where, let's just say that a new vulnerability is discovered in bind. And a worm is written to exploit this vulnerability in an automated way, and it does not bother to obfuscate itself through any of these mechanisms that we talked about. You might, if the Snort community, which of course is releasing signatures all the time, if the Snort community can come up with a good signature for what this packet looks like on the wire, that might make a really good candidate for something you might want to define is not something suitable to talk to a local socket. And furthermore, if the vulnerability discovered in a server, say bind, in a production environment that you can't easily just take down and patch because you have to schedule an outage window because of lots of layers of management around your IT infrastructure, you may not have any other really good option. You may really have to deploy a response mechanism in order to not be impacted by such a worm. Okay, so the Snort signature set's pretty large. We don't want to have to sit there and try to muddle through parsing that signature set and translate it into equivalent iptables commands. That's where fwsnort comes in. So it does as good a job as it can by parsing the Snort signature set and recasting it as iptables commands that match as closely as possible to what the Snort rules themselves are doing. There are lots of exceptions to this. This is not a clean translation cases, but in some cases you can get pretty close, and we'll have some examples of those in a little bit. So all fwsnort rules that it builds, of course it can be in the multiple thousands now that you're running within the kernel, are placed within custom defined chains that are interfaced via the built-in input, output, and forward chains in the filter table. And it does this to maintain a strict separation between any existing iptables policy that you may already have on the system, so that you can deploy fwsnort in parallel and not have to worry about it messing up your existing policy. About 60% of all iptables rules in the Snort 2.3.3 release, which is the last release of Snort that contains a GPL'd rule set, can be translated. The 60% translation rate, incidentally, is up about 10% from the previous release. So in the current release of fwsnort, which is 0.9.0, it now is able to translate Snort rules that make use of multiple content matches because the iptables infrastructure is so good now that it allows multiple matches per rule. And we'll see some examples of that shortly. Yes. So absolutely. So the question, I'm sorry. Okay, so the question is, this is inline, and the answer is yes, absolutely. iptables being a firewall by definition is inline, unless you're, connected to a span port on a switch or something, and you're just sending packet data its way, but you probably aren't deploying iptables in that way. So yes, it is inline, and so the question also is, isn't there a performance impact? The answer is yes, absolutely. If you are tying the forwarding or communication of packet data to an additional operation to inspect application layer data via an algorithm, you are going to add some latency. And you will see that IPS vendors out there who have devices that are doing the same kind of thing will sometimes publish latency numbers in terms of microseconds that it will, in additional, this additional inspection occurs on the network. Of course, these numbers are very, very difficult to come up with. I mean, if you drill down there, you have to ask them things like, well, what's the size of your signature set? What are the size of the packages you're running across the network? What is the average bandwidth utilization in context of the IPS itself? I mean, there's all kinds of variables that go in there. The short answer is yes, there is some additional latency. That's why the Boyer-Moore algorithm is used, which is very fast. And also, if you're, I would say that the best way to deploy fwsnort, in my opinion, is for those kinds of things that you're really concerned about. For example, those new vulnerabilities that may be discovered, and you can have a low or small signature rule set for which the additional latency is practically not detectable. I mean, it's just extremely, extremely fast. So some other things that fwsnort does, it emulates the home net and external net variables that you're familiar with from the snort configuration file. There's a few others in there as well. Reporting is done via the log target. Remember that we're running all these rules directly in the kernel itself, so it doesn't have any user space processing capabilities available to it. It can't send out emails or generate reports for you or something like that. It just takes advantage of the existing capability in iptables to generate logging messages. So you will see a little bit later on that you can communicate some useful information via signature match, and this can be analyzed with psad, which is a userland application, which does have email reporting and a few other things like reverse DNS lookups and who has lookups, etc. So fwsnort, any intrusion prevention system, anything that has the capability of application layer, responding to application layer attacks should, and if you're interested in this kind of thing, you should be asking, does it offer the capability of whitelists and blacklists? So if there's a particular class of network traffic that you just don't want this device to have any possibility of messing with, that's something you would add as a whitelist. Consequently, or conversely, also if there's a particular IP address that is misbehaving a lot, you might define as within a blacklist rule. And these are implemented via the return targets for whitelists, as well as the drop or reject target for blacklists. So as of the 0.9.0 release of fwsnort, it now takes advantage of the comment match. And the comment match allows you 256 characters per iptables rule to put directly within the kernel itself, sort of as a tag, if you will. So fwsnort uses this to put, for example, the snort message field directly within alongside an iptables rule, and I'll show you some examples of this in a little bit. That's useful because if you're doing a list on your iptables rules and you've got this really complex looking set of application layer matches and protocols and ports and IP addresses that you want to match against, it can be kind of hard to figure out what's going on in an individual rule. So conceptually, if you think about how iptables interacts with packets in the kernel, this is a very basic diagram. There's lots of things that are not depicted here, but basically the three red boxes are the input, output, and forward chains that are available in the filter table. All three of these chains are interacted with after a routing decision is made by the kernel. So the kernel says, okay, I've got a packet off an interface. I now need to see, this is an IPv4 packet, for example. I need to see where it's destined for. The kernel makes a routing calculation to see whether or not it's destined for a local socket or should be destined for a system that's connected via, say, another interface, so it should be forwarded through the system. Any packets that are destined for local sockets are sent to the input chain, and on the way up, the application can make use of that packet data, do whatever to it, make a response. Responses are compared against the output chain and then on and forwarded through the system. So how does fwsnort interact with this? Well, in the forward chain, remember that this applies to packets that are to be forwarded through the system, so they never actually talk to a local socket. Packet comes in off an incoming interface. It is jumped immediately into the fwsnort forward chain, where three things then take place. First, whitelist comparisons are made. If you've defined a class of traffic that needs to be never messed with or even inspected by fwsnort, the packet is then hit against the return target, and so it's returned back into the forward chain for further processing for whatever rules you already have there. Packet is then, if it doesn't qualify as belonging to a whitelist, a blacklist comparison is done. So if you define this IP address to be something you never want to be able to communicate through your system, it is dropped immediately and no further processing is taken. And then next, a set of rules in the fwsnort forward chain that correspond to snort rules that do not have the flow keyword. So we're not doing comparison against established TCP connections, for example. And then finally, an fwsnort is stab chain, and this is where all the rules are placed that do require some sort of do require an established TCP connection in order to be able to inspect against those particular rules, again by the flow keyword in the snort rules language. So down to some specifics. These are some example signatures. I've divided this one signature here into two blocks. The first line here is the snort rules header. You can see that it defines any communication from an external network to our HTTP servers over HTTP ports. So these are transport layer and below characteristics. And important things to note here are the flow and content keywords. This is a simple signature, just looking for somebody providing the string inmap %20 to our web server, presumably through some CGI interface, in an attempt to execute the inmap scanner via our web server. Sort of an interesting signature. Maybe not too practical. You might get a lot of false positives potentially, or somebody might just sort of think it is fun to include that in one of their CGI queries. But you can translate this rule. This is the fwsnort representation of what it would look like. So this is a single iptables command. I know it's a little bit obtuse looking, but what it does is it adds the rule to the fwsnort is stab chain. Remember that the flow keyword is set in this rule, so we're looking for content over an established TCP connection. This is in the forward chain. It also adds a similar rule to the input chain for the local firewall itself, but in the forward chain we're looking for a destination port of 80 over the TCP protocol, and the most important thing is this -m string command line argument, which defines a string to look for in application layer data, and the next argument, this -algo bm here, stands for that communicates to the kernel that you want the kernel to use the Boyer-Moore algorithm to inspect this particular rule. And finally, you can see example of a comment match being used here to take the message field from the snort rule itself and put this within kernel memory. You can disable this if you like, of course, to save kernel memory, but it really isn't that much. And you see the message field, web attacks inmap command attempt, followed by the class type, it's a web attack, the revision number from the snort rule itself, and this FWS 0.9.0 is the fwsnort rule version number. And finally, so this rule, what is it doing? It's actually not taking any action against this packet if it matches it, this signature. It is just going to log it. It's saying here, this bracket 1 refers to the rule number within the fwsnort chain itself, followed by the snort ID number, which is 1361, and this string is stab means that fwsnort matched the packet within an established TCP connection. Yes, question?
I know that this is a pretty simple example, but the downside to this is if that string, that could get matched even into the request body or the response body, right? I mean, that's searching the entire, this specifically breaks it's the entire thing. It isn't just a query. If it's outside the query, it would get matched.
Yes, absolutely. So the question is, if this is outside of the query, this would get matched, and the answer to that is yes. I mean, at any point, if this string exists in a packet that is being sent with the destination of this 192.168.10 class C subnet through the forward chain, presumably this is coming from a client going to your server, but you can't guarantee that. Remember, this is an approximation, so absolutely. So if that string is seen within that packet, it will match. I should note that the string match extension in the 2.6 kernel series supports depths and offsets, so you can restrict, if you'd like, via, again, an approximation to say that you only want this string to match if it exists in the first 10 bytes or 50 bytes or whatever you define. using Snort itself to guide us for what we should be looking for. So, you're seeing, in Snort, we're doing lots of complicated things like, you have preprocessors that are there. You have the ability to mitigate and take into account complex application layer encodings. You don't get that with iptables, absolutely. And you probably never will. It is a firewall fundamentally, but it's interesting to consider that some packets may look malicious enough within basic characteristics for us to define that we should at least log them or drop them. So moving on to a little bit more complex example. This one uses multiple content fields which are now supported by fwsnort. So the Snort rule here looks for, this is from the Bleeding Snort signature rule set. The first string it looks for is pack die exclamation point, and then followed by this sort of obtuse looking hex block of hex codes. It turns out that translating hex codes is not an issue for iptables. I contributed a patch to iptables to allow you to essentially lift the content fields directly from Snort rules that contain hex codes within these pipe characters verbatim. You don't have to go through some sort of translation to get that to work. They just come directly out of the Snort rule with this hex string option in the iptables command. And as you can see, we're again using the comment match to input the message field and some other information, even the URL for a reference for where this attack came from or derived from, the information about it directly within kernel memory. And our rule count is getting a little bit higher here. You can see 640. So this is rule number 640 within the fwsnort chain. Similarly for UDP, getting a little bit short on time here. I'll try to speed this up. So here's a UDP signature, a little bit more interesting because you have both source and destination port criteria. That, of course, is easily and faithfully translated by iptables because transport layer criterion below is quite complete in iptables, being a firewall. Snort rules can get long, and your iptables command also pretty long, but it does handle it. Okay, so rule options that are supported to at least some degree within iptables. The top three in the left-hand column are the most important. The Snort rules header, of course. I mean, these are not specific keywords, but that are in the body of the Snort. At least it allows you to define source and destination IP addresses, protocol, and source and destination port numbers. Content field, of course, and the flow keyword. And then here's a bunch of others that also are supported by iptables. There's the flags match against the TCP protocol. You can specify offsets and depths now within the updated stream match extension in the 2.6 kernel. Desize can be emulated with the length match. ICMP types and code values, TTL and type of service bits with the TTL and type of service bit matches. And down here, this last one, this response keyword, if you've got the flex response detection plugin running in Snort so that it can generate session busting traffic like a TCP reset ACK for a TCP connection, etc. That, of course, can be emulated with the reject target in iptables. Okay, so any discussion of this is not going to be complete without what can we not emulate to any degree really within iptables. Well, first and foremost, a lot of signatures these days are using PCREs. There is no Perl PCRE engine within the kernel. So trying to characterize network traffic or attacks that use PCREs is a particular challenge that we will not be able to solve until somebody decides to put a PCRE engine into the kernel itself, which will probably never happen because you can construct some PCREs and pathological data designed to exploit those PCREs such that the runtime for that data is in the thousands of years. You don't want to make it easy to crash your entire kernel just by wafting a maliciously constructed packet past an interface. Flow bits is another one. You can kind of do some things around this using the connection marking capability in iptables, but it's not really there yet. This is a capability that allows Snort to communicate information across signatures, and doing that within iptables would be pretty difficult. The byte test and byte jump keywords are kind of interesting. The 2.4 kernel can actually emulate these to a greater extent than the 2.6 kernel, because the U32 module used to be able to emulate a lot of this capability, but that same skbuff structure difference that I mentioned earlier has broken the U32 for the 2.4 kernel series right now, and there is not yet a 2.6 port of it. That's a good open source project if anyone is a kernel hacker out there. So there are some other fields I think that are interesting to at least consider. All of these have no explicit support within an iptables match to be able to match on them directly. So you can't write a rule saying I only want an iptables rule to fire if the ICMP sequence value is 10. You can't currently do that with iptables, but at least it is included within iptables logging messages, and so are even things like TCP sequence acknowledgement numbers if you use the log TCP sequence command line option. And there are a few others as well, Snort rule options that we can't really emulate, but some are logged again. So just a couple of example log messages here. This is a TCP log message generated by fwsnort for rule ID number 1361. It is added to the fwsnort input chain. I'm sorry, this is the forward chain, as you can see by the fact that both, I'm sorry, wait a minute. This is the input chain because the output interface is not defined here, and it's over an established TCP connection. Down here, I'd like to emphasize this. This is the options of the TCP header by using which is included as a hexadecimal block. It isn't decoded for you, but at least it is logged. So if you were to ask the question, well, what is our header coverage? You know, how close can we get here? The IP header is something that you're seeing here. This is a graphical representation that shows the portions of the IP header that are logged by iptables. The dark gray boxes are logged by default. The white boxes are not logged and have no possibility of being logged because the logging infrastructure in Netfilter doesn't support it. And the sort of this medium gray box here, IP options can be logged by iptables but you must supply the log IP options command line argument to your logging rule. TCP header coverage, similarly. Source and destination ports, of course. TCP size. And most interesting to me is the options portion of the TCP header, and the reason for that is because passively fingerprinting an operating system via a TCP send packet or ACK packet or reset packet requires looking at the options portion of the TCP header, and POF is probably the best example of a mechanism that does this. UDP, similarly. UDP header is very simple. It's only 8 bytes long. Source and destination port numbers and the length values are logged by default. And there are no command line arguments to iptables to get it to do anything different with UDP headers because they're so simplistic. The checksum is not logged and will probably never be logged. ICMP. ICMP type, code, ID, and sequence are logged here, as you can see in bold at the bottom of that rule. And ICMP is kind of interesting. You have both the ICMP type and code values are logged. Checksum, again, is not logged. And the data corresponds to which type and code was set in the packet and is logged to some extent. If you want details on that, look at the ipt_log.c file in the Linux kernel. Okay, so any questions at this point? psad is an iptables log analyzer. It offers both email and syslog reporting. It integrates well with fwsnort, as we'll see here in the demonstration. It offers dshield integration, and a relatively new feature added in the 2.0 series is the ability to visualize iptables logs by interfacing with the Afterglow project. Offers built-in passive OS fingerprinting, assuming that you've used the log TCP options command line argument to your logging rule. And it also decodes IP options for you. It can do things like detect source routing attempts that way. And of course, it detects many of the port scans that are generated by InMap. And it offers timeout-based auto-blocking rules if you choose to enable them, and they can be limited to Snort signature matches that came over only established TCP connections. So at least somebody can't just use a stick or snot style attack to fool fwsnort into generating a signature match and then psad with the go and block an IP address. Okay, so the Honeynet project releases scan challenges periodically. They're really interesting challenges where they would stand up a Honeynet and hope that it is compromised, and when it is, they release data from those compromised events to the security community for analysis. And if you look at scan number 34, you will see that they release about 39 megabytes worth of iptables logging data. The Honeynet addresses have been sanitized to 11.11 list class B in the data, as we'll see. And incidentally, there's a portal now by Raphael Marty, that the same author that wrote Afterglow, called secviz.org. Check it out. There's lots of great graphical representations of security data up there, everything from PCAP files to Snort, alerting logs, etc. Okay, so I knew that this was a Honeynet, so hopefully there were some compromised boxes in there. I used psad in the CSV mode to parse the iptables log file, this 39 megabyte file, and I told it that I wanted to graph only the source, destination, and destination port values such that the source address came from the Honeynet. So what I'm trying to get at here are outbound connections from the Honeynet, which might indicate a compromised system. I'm taking this output and I'm piping it through Afterglow for rendering. And the result is this. This may be kind of hard to see here, but the slides are on my website if you'd like to see them in more detail, but I'll point this out. All Honeynet addresses are in yellow. These are IP addresses. All red boxes here are external IP addresses that do not lie on the Honeynet. And all the blue circles represent port values. So you can see up here at the top right that here's a bunch of systems on the Honeynet that aren't doing very much. They're talking to a couple of external systems, but there's not a lot of activity there. But this one box down here at the lower left is making an awful lot of outbound connections. And if you, I know you can't see this on the slide here, but this port is 6667 IRC. This port is 22 SSH. So this machine is talking both outbound, making outbound IRC connections and outbound SSH connections. That's pretty suspicious. And so I didn't have to ask complicated questions to try to get that data. It's just I've got a really, really easy way to graphically represent this data, and something that just stands out immediately. So this might be a way to focus your efforts on something that is interesting from a security perspective. Similarly, the Nachi worm uses a 92-byte ICMP payload, and here I've asked psad to parse the iptables log, look for source and destination. So the output contains both the source and destination IP address and the IP length field within the IP header, only if it matches 92 bytes. And I've supplied an additional regular expression here to limit the parsing output such that only ICMP type 8 packets are included in this output, as you can see. And the result of that, so you can see lots of external addresses ganging up on the Honeynet addresses. This blue circle here is the 92-byte IP length value. Okay, so if you are running a project that's providing iptables log data, please, I have a couple of requests. Use the log IP options, the log TCP sequence options, and the log TCP options command line arguments to your iptables logging command. This will mean that your data will be a lot more complete. Fields that aren't logged by default will now be logged, and you can do things like do a passive OS fingerprinting calculation against those logs, and other types of attacks can be detected just because your logging output will be more complete. Okay, so demonstration. I don't know if if people in the back can see this, but okay, first I was going to do a VMware kind of thing, kind of cool with virtual machines and all that, but I'm just going to go old school here and use a loopback interface. Sorry. So the first thing I'm going to do is just connect to, I'm running a local web server on this machine, and here is my website. As you can see, there's stuff there. So the first thing I'm going to do is I'm going to instantiate an fwsnort policy that contains a signature for this Tomcat snooping signature defined in as the web MISC category within the Snort signature rule. So this is against the Tomcat server. And this is the result of an iptables list. You can see that the fwsnort forward estab chain as well as the fwsnort input estab chain contains this rule here. And up here is a tail minus f on the log via syslog. Both psad and fwsnort now are running. And I'm going to make a web request for the data that matches the content of that rule. And what comes up here, you can see that, first of all, fwsnort did not interfere yet with this communication, because we got a legitimate response from the web server saying that this URL was not found. But in the log, we got a signature match. Oops. So this is the iptables log message that contains the prefix derived from the fwsnort rule. psad picked that up and gives you a little bit more information just in your log. Also, an email alert is generated saying what the snort message field was, the snort ID number, and the fwsnort input chain, and the rule number. So if you're getting if you've got a long fwsnort policy and you're getting lots of signature matches on a particular rule, for example, you can always narrow it down to which specific rule number was causing the matches by virtue of these logging prefixes. Okay, so let's be a little bit more punitive now.
Syslog.
So the question is, does psad just basically tail the syslog? Actually, psad reconfigures syslog to write to a named pipe, and it acquires all of its logging data after an inspection of the data that comes across from that named pipe. And so it writes a specific logging file that contains only iptables logging messages. You don't have to go through and try to grep them out of your syslog. Yes? psad has a watching daemon called psad watchd. If the PID ever dies, it comes back. But the answer is no. I mean, if the named pipe is just a construct that doesn't require an additional process. I mean, it's just essentially a file that it opens. So it's not, even if psad were to die, it's not going to kill syslog. Okay, so now this policy reject target against that same signature and logs it at the same time. In this case, you can see the log message is generated, but Links is unable to communicate with the web server itself because we received a TCP reset. Incidentally, here's another opportunity for some open source development. The reject target cannot generate packets against both sides of a TCP connection currently. It can only generate packets against the source address that matched the iptables rule. It's not so bad because iptables at the same time is not going to forward a packet that matches the reject target, but if an attacker were to have, so you might think that an attacker with a kernel level filtering mechanism can filter the incoming reset and then just ignore it and TCP would never know. But because we're dropping the packet, the TCP connection is not allowed to proceed. But it would be just kind of nice to have the ability to also send the reset to the server side too. Okay, so one more example here. So this is a DOS attack against a syslog server associated with Cisco devices. So I've instantiated this rule set within the kernel, and now I'm going to send the attack across the wire. Note that, of course, generating non-printable ASCII data from the command line is quite easy with Perl. Here's the Perl command that you would use in order to be able to generate something that's non-printable. Actually, these are all printable characters, but frequently it's contain things that aren't printable. And finally, note that I didn't have to start a server in order to be able to get that signature match because this is a UDP-based attack and therefore requires no notion of a connection. But I'm now going to use netcat to actually spawn a server on port 514, a UDP server. Actually, I'm sorry. Getting a little bit more punitive again here. So now I've got a server listing on port 514 that I could reconfigure to iptables to log the signature match, but also drop the offending packet. So I can send the packet across again. Let's see. 4. That's strange. Doesn't matter. Okay. Signature match connected, but note we never got any data to our server, and that's because iptables use the reject target, which also drops the packet. So the server never had an opportunity to see that attack. Oh darn. Shameless plug here. I've written a book about this topic. Actually, I'm almost finished with it. Hopefully it'll be released in maybe July. Linux Firewalls, Attack Detection and Response, published by No Starch Press. Questions? Yes?
So why would you do this other than to be doing it at a lower level than what Snort can do most of the time?
Yeah, so the question is, why do this? Why, other than doing this at a lower level within the kernel, why not just use all this? Well, so there aren't many good answers for that. Of course, Snort being the 800-pound gorilla is something that you would almost always want to run. But the network fragmentation example is one case where I can think that this might be important. So if you don't want to always have to worry about reconfiguring frag3 to account for the fragmentation algorithm of your end host, iptables can be a way to not have to worry about that because you are running the defragmentation algorithm of the IP question. Secondly, if you want to do something really fast and not have to worry about copying packet data from kernel memory into user space, then and you're doing and this is the inline case note. Then this can be useful. So particularly if you have a particular kind of attack that you just a single attack that you really don't want to make it to a local socket, and you want that to be dropped as low as possible, as quickly as possible, that's where this is handy. You would get additional. Doing that within the kernel directly will be faster than what Snort can do because of the copy problem between kernel and user. Any other questions? Yes.
I just want to make a comment. It seems like that this would be, maybe I'm just rephrasing what you already said, but it seems like this would have the potential to put on your end hosts on your individual server rather than if you had a firewall or load balancer in front of them. It seems like putting it on the end node, on the leaf nodes, there's more potential in conjunction with Snort running somewhere else.
Absolutely. So that's a good point. And the point is, it seems like this. He was saying this. It seems like this would be more useful to put on individual end hosts on a network as opposed to having it, say, as a global within a policy where forwarded through to an internal network. I think that's very accurate, and that's one of the reasons that I brought up the fact that in the recent Linux kernels, the stream mask extension is enabled essentially by default. You probably already have this capability. All you have to do is run iptables commands. You don't have to sit there and deploy or Snort inline to be able to take advantage of that. You can just run a single iptables command for something that you've defined as, or the Snort community has defined as being malicious to take advantage of the same protection. Yes, Hank.
That don't things like that require a PCRE engine, and you don't want to put a PCRE engine in the kernel. Have you looked at doing things like using the ulog target or maybe a netlink to, once it's passed the first subset of tests that are built in, pass it off to a helper that's in user space?
Yes. So the question is, so have I looked into for more complex rules, like for example the PCRE rules that are in the Snort rule set? Would it be possible to make use of, say, like a preliminary match, and then make use of, say, netlink sockets, or perhaps the ulog target in Netfilter, in order to be able to get some processing at first and then do more complex processing at a higher level? Is that the question essentially? Yeah. Okay. So yes, I mean you can envision scenarios where Snort itself doesn't want to make use of PCREs very much, right? I mean, they're performance intensive. You want to minimize the number of PCREs that you have to use. So one way to do that is in the Snort rule itself, is to have a content match of a static string that does sort of a pre-qualification of a piece of what might be malicious data before it's passed on to a PCRE match. So I think that's an excellent point. I think there's nothing that would prohibit that, because you can combine. I mean, Snort inline itself makes use of iptables rules via the Q target. So what you could do is you could combine the Q target rule with an fwsnort rule set, such that the fwsnort is doing sort of the matching before anything actually gets to hit the Q rule, and if it passes all those tests, then it could hit the Q rule for further processing by Snort. Could be a way to speed up Snort inline in certain cases, I would say, potentially, yes. I haven't done a lot of research in that area yet, but perhaps. So, any other questions? Well, thank you very much. Hi. Hi, Mike Rash.
It's really kind of scary to hear you describe this, because the project I was just working on, we weren't using Snort, but essentially we took Indian firewall and modified it to work on
Which firewall?
Indian.
Yeah.
Yeah.
Okay. It's ENDI. Yeah. Okay.
Modified it to work on Linux, because it was basically we want specific requirements to use Red Hat, and of course it comes kind of with its own personalized
Oh, thanks.
hardened OS
Okay.
out of an install.
Yeah.
And we basically did the same thing with the nameplate. So it's really just interesting to see that.
Oh, cool. Awesome.
Kind of wish we'd known about your stuff earlier. Probably would have saved us some development.
Well,
It's if I can feed some
great. It's all free and open source, so please.
question. This may be a movie question.
Absolutely.
How would I get it to maybe take it from iptables and send it directly to a MySQL?
The ulog target itself has support for doing that. So if you look at the ulog is a target that allows you to essentially have handlers that will write data from iptables out to various things. It can even write PCAP format, and one of the things it supports is the MySQL interface. So you could just put your rules into directly within iptables with a ulog target and tell it where you want it to write it, and the MySQL handler would take care of that for you. Yeah, sure.
There you go.
What's up? How's it going? Good to see you.
Nice to see you too.
Oh, thanks. Thanks. Well, it's I mean, we are sort of a competing, we are putting, we have a partnership with Whitelists, for example, so we're already, making use of this one from that perspective. So, so this is kind of an open source, side thing. Sorry, get out of your way here.
That's okay.